Hello, welcome to part 2 of our Chapter 13 lecture on fluids. In this part of the lecture, we will be looking at buoyancy and Archimedes Principle. Let's start by talking about the buoyant force. We can think of starting here with a little demonstration, or at least imagine a demonstration, where we weigh something dry and then reweigh it underwater. So suppose we have some chunk of material here, let's say it's a block of metal, and we hang it from a spring scale like the one we've been using in this class, and it has a certain weight. Now what happens if we lower this object in the water? What do you think happens to the weight here? Well, it turns out that objects weigh less when underwater. So for example, let's say this piece of metal here has a weight of 7 pounds dry. When we lower it into the water, you can see its weight reduces to say something like 4 pounds. Now the question is, why is this? Why does something weigh less underwater? Well, the answer has to do with something called the buoyant force. So to get a grip on what the buoyant force is and what buoyancy is all about, let's consider our object here. Again, this is maybe our piece of metal that we're weighing in the water. Remember that water or any fluid has pressure, and that pressure increases as we go farther down into the fluid. So on the top of this piece of metal, there is a force due to the pressure at this place, and so we'll call this F sub top. And that's the due to the pressure at the top. And then likewise underneath here, there's going to be a force from the pressure pushing up, which we'll call F bottom. Remember that pressure pushes in all directions. Now, of course, there are also pressures pushing left and right, but those are going to cancel each other. For every force pushing to the right over here, there would be an equal and opposite force pushing to the left. But these two forces here do not cancel, because remember, the farther we go down in the fluid, the greater the pressure is. So this force down here, the bottom force, is actually larger than the top force. And this is the origin or the source of what gives something buoyancy and makes it weigh less. Now, of course, this object also has the force due to gravity, which, as always, is equal to mg. So this is mg is the dry weight. But underwater, we have these two other forces working here that tend to reduce the weight of the object. So again, since the bottom force here is greater than the top force, we can define the buoyant force as the difference between the bottom force and the top force. So we have F bottom minus F top, and this is what we're going to call F sub B, where B is for buoyant force. So the underwater weight of this object, if we replace these two arrows here with their equivalent buoyant force, which is going to push up, we have weight down, mg down, and we have the buoyant force, F sub B, pushing up. So the underwater weight is mg, which is the dry weight, minus F sub B, which is the buoyant force. So this F sub B reduces the weight of an object when it's underwater. And by the way, we can look at this free body diagram here, and we can predict that if the buoyant force here, F sub B, is less than the dry weight force here, mg, then mg is going to win the battle and this object is going to sink. On the other hand, if this buoyant force here happens to be greater than the dry weight of the object, then this object is going to float. And so this is what actually determines whether an object sinks or floats. We can now do a calculation of the buoyant force, and this is somewhat similar to what we did in part 1 of this video, where we calculated the change in pressure due to depth. what we're going to do here is, here's our object. And just to make things easy, we're going to assume it's a rectangular shaped object here. It turns out that it absolutely doesn't matter at all when we see our final result. It doesn't matter what shape we chose, but this is certainly a much simpler shape to deal with here. So if we kind of look at the geometry of this picture here, we've got this object here submerged in water. This is the surface of the fluid up here, or the water. And so the top surface of this object is a distance or a depth h, and this is a lowercase h. The bottom here is down another distance, which we'll use an uppercase h. That's the height of our block of material. So the entire depth of the bottom of the object is little h plus big H, and so that's the depth down here at the bottom. So this pressure force at the top, remember that force is pressure times area. So we're going to use our result from part 1, where the pressure force is equal to P naught, that is the atmospheric pressure, plus rho g little h, all right, that's the depth right here, and all of that multiplied by the area of this object here, okay? And by the way, rho, remember, is the density of the fluid, okay? And now on the bottom, we do the same thing. This upward force due to the pressure down here is equal to the pressure at the bottom times area. And again, we have P naught, which is again atmospheric pressure, plus rho g, and then here the difference is our depth from here all the way to the top of the surface here is little h plus big H. And then all of that in brackets is multiplied by A. So the buoyant force, remember, is the difference between F bottom minus F top. And so if you take all of this, all right, and subtract all of this, you'll see that most of the terms actually cancel each other out. Remember, this A has to be distributed inside of all these terms, which I don't show here. The only term that remains is this big H here, because you can see everything else matches the same up here. But this big H, this uppercase H here, which by the way is the height of our object that we're weighing, that is the only term that remains, and of course it's multiplied by rho and g and A. So here is our buoyant force. It's density of the water times g, 9.8, times the height of the object times the area of the object. Now, the height of the object here, h, times the area of the object here, gives us the volume of the object. Okay, so we can replace HA with volume. And another trick we can do here is that we know that the density of the fluid times the volume of the fluid that was displaced by this object is equal to the mass of the displaced fluid. All right, because remember again, mass is equal to mass density times volume. So we can put all of this, we can substitute this up into this equation here. So we have rho, the density of the fluid, all right, is times the volume, here's the V, is equal to the mass of the displaced fluid. So this simplifies things quite a bit. We can replace the rho and the V with m, the mass of the displaced fluid, times g. So look what we've got here. The buoyant force is equal to m times g. Well, we know what mg is, that's weight. So this is mg for the fluid that's been displaced by this object. So after all of this work here, we come up with a relatively simple result. The buoyant force is just equal to the weight of the displaced fluid. And what do we mean by displaced fluid? Well, that's the amount of fluid that was pushed out of the way when we submerged this object into the fluid. Okay, so in other words, if this level of water here was right up to the top of the bucket before we put this in here, when we submerge this object into the fluid, then some of the water is going to spill over. Well, the amount or the weight of that water that spills over would be equal to the buoyant force, according to this calculation here. And by the way, this is known as Archimedes Principle, which we're going to talk about next. So Archimedes principle, we can sort of break it up into two parts. The first part is basically what we just proved a couple slides ago, and that is the buoyant force exists and it's equal to the weight of the displaced fluid. So this is, by the way, this is the great Archimedes from ancient Greece. He lived about 2,000 years ago. One experiment that I did in the lab here, which I'll just show you the results here, is I took a 1 kilogram mass and weighed it on a Newton scale. And we know the dry weight of 1 kilogram should be 9.8 newtons, right? Because the weight is equal to mg. So if we take 1 kilogram and multiply it by 9.8, which is g, we get 9.8 newtons. So I will dip this now into a beaker full of water, and this beaker starts with exactly 300 milliliters. You can read that on the side of the beaker. So what happens when I dip it into the water is there are two effects here. First of all, we see that the weight of the object is now decreased. Instead of weighing 9.8 newtons, its weight has dropped to 8.7 newtons because of the buoyant force. All right, remember that objects always weigh less underwater. But more importantly, for what we're going to do here now is I noticed that the water moved up a total of 115 milliliters. Okay, now remember that the buoyant force is equal to the weight of the displaced fluid. So the weight of the displaced fluid is the mass of the fluid times g. So the mass of the fluid, well, remember that in using the metric system, it's really nice. Each milliliter of water weighs exactly 1 gram. So 115 milliliters is 115 grams, or 0.115 kilograms. So that's the mass of the displaced water. All right, when I dumped this 1 kilogram weight in there, it pushed the water up by a total of 115 milliliters, and the mass of that is 0.115 kilograms. When you multiply that by g, which is 9.8, you come up with a force, a buoyant force of 1.1 newtons. So that means the water is pushing up on this object by 1.1 newtons. So if we take the original weight of 9.8 and we remove 1.1 newtons from that, right, because that water is pushing it upwards, we get the weight, the underwater weight of 8.7 newtons, which, so everything works out correct. This is Archimedes' principle. And, again, amazingly, this was figured out by a guy, well over 2,000 years ago in ancient Greece. Here's another way to look at Archimedes' principle that may make it a little bit simpler to understand. So it's pretty much the same experiment. Suppose you take a piece of metal and you weigh it outside when it's dry, and in this case, let's say it weighs 7 pounds. Now notice our bucket of water here. Right at the top of the water, we have a little hole with a little spigot. So any overflow can flow out of here and be collected in a little pan down here. So when we dump this, when we drop or lower this weight down into the water like here, the water level has to move up because some of the water has been displaced. And all of that water that moves up has to flow through this tube and go into the little bucket here. So if we look at the scale here, it weighs now 4 pounds instead of 7. So that means the buoyant force must have been 3 pounds pushing upward because gravity is pulling down with 7 pounds. But that also means that the amount of water that was collected in the bowl here is equal to this force. Okay, so the weight of the water here, 3 pounds, is equal to the buoyant force of 3 pounds. There's a second part of Archimedes' principle that is basically sort of a derivative of part 1, and this says that a floating object displaces an amount of fluid whose weight is equal to the object's weight. So if we take our bucket of water here and we, let's say we float a block of wood here. Okay, so this is something that doesn't sink. It floats on top of the water. So if we look at the free body diagram here, this object now is, motionless. It's in equilibrium. So the downward force is the mass of the object times g. That's its weight. The upward force, remember the buoyant force, is equal to the mass of the fluid times g. And these two forces are equal to each other, all right, because of equilibrium. So, and remember that, again, that the buoyant force is equal to the mass of the fluid. It's the weight of the fluid, basically, displaced by the object. So this again tells us that a floating object will displace an amount of fluid whose weight is equal to the object's weight. The mass of the fluid that's been displaced is equal to the mass of the object that's floating in the fluid. So Archimedes' principle also this gives us another way to look at whether or not an object will float or sink. We looked at this a little differently earlier when we talked about buoyancy and the buoyant force. Another way to think of this has to do with the density of the object. So if the object that we put in the water has a density greater than the density of the fluid, then the object will sink. Okay, so if you put a piece of metal into water, or you put a stone into water, well, a stone or metal has a higher density than the water, so it will sink. On the other hand, if we put something in the water that has a lower density than the fluid, all right, so rho of the object is less than rho of the fluid, for example, wood or styrofoam or something like that, then the object will float. The third case is where the object has the same density as the density of the fluid. And in that case, we have what is called neutral buoyancy. So in this case, the buoyant force and the weight of the object are actually equal, and the object will just sort of hover in the water without sinking or without floating. And interestingly, this is something that fish do to hover in the water. They have something called an air bladder inside of their body, and they can contract or expand that air bladder using their muscles. And that allows them to change their density to make it the same as the density of the water, and therefore they can just float at a certain position in the water. And by contracting or squeezing or expanding that air bladder, they can move, they can actually float up, or they can sink down. Our last slide in this part of the lecture is sort of an interesting application of Archimedes' principle, and this is the determination of body composition by underwater weighing. This is a test that is used by kinesiologists and sports scientists and personal trainers and so forth to determine the basically the body composition, the percent body fat of typically an athlete, and this is also called hydrostatic body fat testing. What they do is they basically are comparing a dry weight of the athlete to an underwater weight, and so to do this, the athlete will basically have to expel all the air out of their lungs, and they sink down under the water, and this, you can see this carriage here is connected to a scale shown up here, and they look at the differences in the weights, dry weight and underwater weight. And the reason this works is because of the different densities of the different types of materials that we're made out of. So for example, water has a density of 1 gram per cubic centimeter. Now bone is more dense than water. It's 1.5 grams per cubic centimeter. So bone sinks. Muscle also has a slightly higher density than water. It's 1.1 grams per cubic centimeter. So muscle also sinks. Fat, however, has a lighter density than water. It's 0.9 grams per centimeter versus water being 1.0. So fat floats, okay? And so by comparing the dry weight and the underwater weight and using, certain formulas and so forth, they can fairly accurately determine the percent body fat and the amount of lean body weight in an athlete. And this is something that is useful for tracking their progress with their training and so forth. That is it for part 2. I will see you guys shortly for part 3 of this lecture. Goodbye.